Alright, hi everyone. Welcome to this video where we'll be learning about the concept of redox reactions. Right, so as mentioned, a redox reaction is actually a type of reaction that involves both oxidation as well as what we call reduction. Now, before we go on further, just to let you know that in chemistry, there's actually this type of reactions that are called oxidation and also a type of reaction that are called reductions. Right, so what we're going to learn here is to understand how exactly could we tell whether a reaction belongs to which particular one. Right, so for this concept, we actually look at four different things. We look at what we call oxidation state, we look at what we call hydrogen, that means the element H, we look at oxygen, we also look at electrons, right? So there's actually four ways to look at this, and to simplify it, we use this acronym of SHOE, right? So for oxidation is where there's an increase in oxidation state, or a loss in hydrogen, or gain in oxygen, or loss in electrons. Later we'll take a look at what this means. And when it comes to reduction, it is just the direct opposite, right? So when you go with this chapter, right, you start first by learning one of them, then just remember that the other one is actually all the opposite in terms of what you're learning. So let's first take a look at oxygen. What does it mean when we say gain or loss of oxygen? In chemistry, whenever whenever a substance gains electrons, sorry for the typo, whenever a substance gains oxygen, right, this is what we call oxidation. And when the substance loses oxygen, that is what we call reduction. So let's use this equation as an example. Focus on this element of Mg, right? If you look at this equation, there's a magnesium that reacted with copper 2 oxide and it formed magnesium oxide and copper. So what we are seeing here is that if you just focus on magnesium as a chemical, take a look at it, it actually gains an oxygen, the one in green highlight. So this is what we mean by magnesium actually got oxidized. So magnesium is oxidized because magnesium gained an oxygen. Let's take a look at the copper 2 oxide. It was CuO over here. In the reaction, what happened is that it just became Cu. So when you look at this substance, we can say that it was being reduced because it lost an oxygen. And since both oxidation and reduction occur simultaneously, that means in this reaction, there's both oxidation and there's reduction. We call this a redox reaction. Okay, let's take a look at another example to try to apply this concept. So remember, when it comes to reduction and oxidation, it is a new concept, but there are various ways to check, and we are learning about using oxygen to check. Let's take a look at this example now. In this example here, we have this thing called iron trioxide, Fe2O3. If you follow the equation, you realize that it became just Fe. So what happened was that it actually lost the oxygen, right? So it lost oxygen, and when it loses oxygen, we call this reduction. So we are applying the concept. Then we take a look at the other one, which is your carbon monoxide, CO. As a reaction happens, you realize that it now becomes CO2. So what happened is that it actually gains oxygen. And when it's gained oxygen, what we call this? We call this oxidation. So how do we phrase this out? We'll say that carbon monoxide is oxidized because carbon monoxide has gained oxygen. Iron trioxide is reduced because iron trioxide has lost oxygen. And since we have both oxidation and reduction happening together, we call this a redox reaction. Right? So you look at the word redox, right? So let me just go back to the first page. The word REDOX actually just stands for reduction and oxidation. So when it happens together, this is what we call a redox reaction. Okay, so coming back to this question, so that is where we use oxygen to help us check whether something is being oxidized or being reduced. But there's also other methods, and we're going to now look at using hydrogen. Now, oxidation happens when a substance actually loses hydrogen, and reduction is the opposite when a substance gains one or more hydrogen. So let's take a look at an example that's over here. Let's focus on this thing called H2S. If you follow the equation, you realize that it became just sulfur. So what happened here was, it was actually oxidized because it lost hydrogen. If you take a look at the element chlorine, and you follow the equation, you realize that it now becomes HCl. So what happened was, it gained hydrogen, and therefore we say that it's being reduced. And since both oxidation and reduction occur simultaneously, this is what we call a redox reaction. Okay, I hope you are following so far. This is the second method in terms of how to look at whether something is being oxidized or reduced. Let's take a look at another example here. Let's focus on, let's say, N2H2, right? We see over here N2H2 actually became just N2. So what we see over here is that there is a loss of hydrogen, right? And based on the table that we see here, losing hydrogen is actually a way to look at whether something is being oxidized. So this is actually being oxidized. Then let's take a look at the other element, which is chlorine, Cl2. In the reaction, it became HCl. So what we see over here is that from here to here, it actually gained hydrogen, right? And we gain hydrogen based on what we learned on this page. This is what we call reduction, or that the chemical has been reduced. So how do we phrase this? N2H2 is oxidized because it lost hydrogen. Cl2 is reduced because it has gained hydrogen. And then, since both oxidation and reduction occur simultaneously, this is what we call a redox reaction. Right, so we'll take a pause over here first. You may want to just stop the video and take a look at the things that you have written down so far, because we learned about how oxygen and hydrogen can be used to check for whether there's an oxidation or reduction. Next, we are going to take a look at electrons, right? So oxidation occurs when substance loses one or more electrons, and reduction occurs when substance gains one or more electrons. Okay, so take note of this thing. So if you go with the equation below, now this part is a bit trickier because you do need to revise your charges and your ions. So for those of you who have forgotten, if you went from Zn to Zn2 plus, this means that you actually lose 2 electrons because electrons are negative and this makes you plus charge. Let's say you go from Cu2 plus to Cu, you went from plus charge to no charge. This means that actually you gained 2 electrons. Okay, this is usually quite confusing for most students, but you really need to take the time to try to revise what's going on in your earlier chapter on chemical bonding. Okay, so another example, sodium. When sodium becomes Na+, we need to ask ourselves what actually happened. So those of us who still remember, sodium has an electron configuration of 281. How does it become stable? It must become 28. So what happened? It lost 1 electron. So therefore, this is what we call losing of electron. Right? So this will keep coming in and out, especially when it comes to this part. So based on this thing, we can tell that zinc is actually being oxidized because it has lost electrons, whereas Cu2 plus has been reduced because it has gained electrons. And since both reduction and oxidation happens simultaneously, this is what we call a redox reaction. Alright, let's take a look at another example. Now we have this chemical called Na plus Cl2 giving me 2 NaCl. If you look closely at the equation, you actually cannot see charges anymore. It's different from just now. Right, just now you could see the plus, the 2 plus over here, right? But now you can't see this in the chemical. So what must you know? We actually need to know that inside this is actually the Na plus and Cl minus. This comes from our chemical bonding knowledge, right? Because this is an ionic compound. So what can we tell here? We can see that this Na actually became Na plus. So it actually lose electron. Therefore, we call this oxidation. Whereas your Cl2 became Cl minus, it actually gained electron, and this is what we call reduction. Okay, and since both happens together, we call this a redox reaction. Alright, so far, right, we are going to move on to the last method now. So if you have finished the notes so far and understand what's going on, good job, because the last one will be a bit trickier. It's this thing called oxidation state. Now I'll just use OS to represent it, but what exactly is oxidation state? It actually refers to the charge that the element will have if it exists as an ion. Right, so it's a bit confusing now, but do take note that there are a few rules that you'll see in the table in the notes. They'll help to guide us, and as we are doing the question, we'll keep using the table until we familiarize with what's going on. Okay, so do take note that for oxidation state, we write it by writing the symbol first, which is plus or minus, followed by the number. Okay, so do take note of this thing as we go along. A couple of rules, so that we're on the same page. Number one, If you are given any element, that means just a normal element by itself, like magnesium, copper, chlorine is an element, Cl2, or even things like oxygen, H2, right? These are all elements. For elements, their oxidation state will always be 0, as you can see from the table. Right? Later we'll look at how this applies in the question. If you have an ion, K+, Cn2+, Cl-, O2-, then the oxidation state will be similar to the charges. So if it's a plus here, it'll be written as +1. If it's a 2+, it'll be written as +2. If it's a 2-, it'll be written as -2. Right? So this is what we call oxidation state. Third, in most compounds, oxygen will always have an oxidation state of -2. So for example, oxygen inside H2O will be -2. Okay, except for hydrogen peroxide, but that is quite rare as a question. In other words, oxygen in CuO, that means copper 2 oxide, right? The oxygen will also be a -2 oxidation state. Oxidation state of hydrogen in a compound will usually be a +1, so hydrogen in water will be a +1, as you can see over here. In general, if the compound has no charge, all these oxidation state will add up to give you 0, but if there's a charge, the oxidation state will add up to give you a symbol of the charge of the ion. Okay, now this sounds very confusing, so let's take a look and apply this whole concept together first. Okay, I won't use these examples here because these are quite complicated, so let me just use something that's more straightforward. First, let's start with water. Based on the rule that you have learned just now, this is a compound. So if I use the notes here, I'm looking at rule number 3. Okay, so in a compound, oxygen is usually a -2, hydrogen is usually +1. In addition to that, I'm also going to take a look at rule 4, whereby the sum must be equivalent to 0. So how does this work? Oxygen in the compound, we know that it's a -2. Hydrogen in the compound, we know that it's going to be a +1. But wait a minute, there's actually 2 of the hydrogen. This would mean that in total, there's actually 2 sets of this, right? And if you were to add up these numbers, right, 2 times a +1 plus a -2, you realize that the total number will be equal to 0. So take note of the rule. Rule number 3 says that in a compound, oxygen is usually a -2, so we follow that. In a compound, hydrogen is usually +1, so we follow that. And rule number 4 says that total when they add up must be equal to 0. So look at this equation, this formula again. Oxygen, there's only one of it, it's a -2. Inside here, each of the hydrogen is a +1, right? And we multiply by 2 because there's 2 sets of them, and overall it's a 0. Okay, let's apply this again to another one. Let's say we call this MgO. In a compound, based on rule 3, oxygen must always be a -2. In a compound, based on the rule 4, total must be equal to 0. So this means that this magnesium here is actually going to be a +2. Because +2 and -2 will give you 0. Okay, so as you continue to do about this thing, you can apply to other chemicals, for example, let's say HCl. Right, so based on rule 3, hydrogen in a compound is usually a +1. Since rule 4 says that total must be 0, that means this chlorine here must be a -1. And in fact, we should know that chlorine is a -1 because it is from group 17. Okay, but so far all this seems quite straightforward, right? Because you can just use simple calculations to solve it. Let's go with something that's a bit more complicated. Let's call this Fe2O3. Now, based on rule 3, each of the oxygen, each of them inside is a -2, right? But in total, if you follow the formula, there's actually 3 of the oxygen. So what this means is that in total, there's actually 3 sets of them. 3 times -2. Since this is a compound, overall, this must be equivalent to 0. So we need to ask ourselves what could be the number here that when we add up with this 3 times -2, we'll end up with 0. Do take note that there's actually 2 of the ion, right? So what this means is that we need to make sure that it's 2 sets of something. When you add together with 3 times -2, will be equivalent to 0. And then you should be able to figure out that this ion must be a +3. Right? So we'll say that the oxidation state of ion is actually a +3, whereas the oxidation state of oxygen is actually a -2. Okay, but of course all these times 3 times 2, right? These are things to help you calculate what's going on. But the oxidation state is each of them, which will be a +3 here and a -2 over here. Now we take this all into consideration and let's go back to the notes, look at something a bit more complicated over here. KMNO4, right? Looks super complex, but remember rule 3 says that each of the oxygen here is a -2. So you see a -2 over here. Because based on the formula, there's 4 of the oxygen. This means that we need to multiply it by 4. Then this will actually give us a total of -8, a pretty big number. Now, potassium here is from group 1, right? And if it's from group 1, we know that group 1 elements will form K+, right? So this is actually a K+ ions, and therefore the oxygen state should follow the plus, and you'll be a +1. So in total, there's a -8, there's a +1, and everything must add up to 0. So what could X, which belongs to M and B? If you do the entire calculation, you realize that X is actually a +7. Okay, so this is how we calculate for this chemical here, KMnO4. Let's look at the one below, NH4+. Right, based on rule 3, hydrogen should always be a +1. But because here got 4 of them, so we times 4. Now if you look at it, this entire ion has a charge here, a positive charge. So this entire thing, when you add up together, the whole thing should have a +1 charge. Therefore, you see over here. So if you look at it, if you play around with your formula a bit, you should be able to realize that the X actually has a -3. Okay, all this comes with practice and practice, right? It won't be so easy to straight away understand what's going on, but we need to apply it. So now that you have learned about oxidation state, right, when we come back to class, we are definitely going to try out more questions to practice it. But for now, let's take a look at what can you do with this thing. After figuring out what is oxidation state, you can actually apply it because oxidation occurs when the substance oxidation state actually increases, whereas reduction happens when the substance oxidation state actually decreases. So what will this look like? Now we look at this example over here. Okay, Zn here is an element, so the oxidation state is 0. Rule 1 says that if it's just an element, the oxidation state must be 0. Copper over here is just an element, oxidation state will be 0. Copper 2+, however, over here, if it's an ion based on rule 2, they must follow the charge of the ion. So in this case, it's a +2. Zinc 2+, based on rule 2, it is a +2. So now look at the oxidation state. For zinc, it went from the case of 0 for the oxidation state for zinc, then it became an oxidation state of +2. So did the oxidation state increase from 0 to +2? It will have, and therefore this is about oxidation. Okay, so now you see how to apply the whole thing. Then we take a look at copper. Copper initially is a 2+, right? Okay, +2 oxidation state. As the reaction happens, it becomes a 0. So what do you see over here? You see that the number dropped from +2 to 0, and this is what we call reduction. Okay, so far, just like for hydrogen, for oxygen, for electrons, there's a bit of working required. And of course, this time round, this one is a bit harder, right? Because you need to really count, follow the rules and everything. So how do we phrase this out? We'll say that zinc is oxidized because the oxidation state of zinc increased from 0 in Zn to +2 in Zn2+. Right? Look at the way it's being written. It's being oxidized, which you should already know now. But we say that the oxidation state of zinc, because this question is about zinc, and where did it change? It went from 0, which is the original one in Zn, to +2, which is the final one in Zn2+. Now this is the way to phrase this kind of writing. Then for copper is being reduced because the oxidation state of copper decreased from +2 in Cu2+ to 0 in Cu. Right? And since both oxidation and reduction occurs, this is considered a redox reaction. I hope so far it's not too confusing. Let's take a look at the next one. Magnesium. Magnesium as an element, the oxidation state will be 0 because it's just an element. That's rule 1. Copper as an element, based on rule 1, is also 0. Then let's take a look at what about the compounds. Right? If you recall, I said just now, oxygen in a compound, right, is usually a -2. So overall, this CuO must be equivalent to 0. So what do you think the Cu could be to give you overall equals to 0? Oxygen is a -2. What must you add in to make it 0? In this case, is to add in a +2. So the copper here is actually a +2. Same for the other side. Oxygen in a compound, based on rule 3, is usually a -2. Magnesium, in this case, overall must add up to be 0, is a +2. So then this gives you a good gauge of the fact that basically in this question, what happened is that magnesium is being oxidized as it went from oxidation state of 0, which increased to oxidation state of +2 in MgO. Take a look at the phrasing. Okay, copper 2 oxide is being reduced, right? Because the oxidation state of copper actually decreased from +2 to oxidation state of 0 in Cu. Okay, so that is how we describe about the reduction. You may be curious now and you might be asking, sure, what about this oxygen, -2 and -2? If there's no change, that means we don't care whether is it being reduced or oxidized, and therefore we will talk about this -2 over here. Alright, so in summary, this shoe method, right, that we spoke about, which is where we will end the video with, is allowing us to check for easy way to know whether there's a reduction or oxidation. Take note that this S refers to oxidation states, right? So it's not just letter S. Oxygen is, sorry, H is for hydrogen, O is for oxygen, and E is for electron, right? So quick recap, for oxidation, there's an increase in oxidation state. For reduction, there's a decrease in oxidation state. For oxygen, there's a loss of hydrogen, a gain of oxygen, or a loss of electron. It really depends on what the question wants or what method you want to use. But for reduction, it's the direct opposite, right? Gain, loss, gain. Right? So in summary, in chemistry, there's this possibility of having something called reduction or something called oxidation. When they happen together, you get this thing called redox, whereby there is both reduction and there is this thing called oxidation happening together, right? But how do we know what is oxidation, what is reduction? We have to use these 4 different methods that you see over here. Either we count the oxidation state, we count the hydrogen, we count the oxygen, or we count the electrons. Alright, so this video will end here, but when we come back to class, we'll run through this a bit more before we go on to the practice questions. Thank you.